Section 3.3 is really one of the biggest sections that we'll have this semester. It kind of takes everything we know about derivatives, including our derivative rules, how we think about slopes, and all these things, and puts them all together in a picture of how the derivatives affect the shape of the graph. So what we're going to do here is think about how can we put all these different things together to draw a nice graph of our function. And you might say, hey, my graphing calculator can do this, but it's really useful because once you can think like this, then you can start thinking in terms of derivatives on how different graphs are shaped and how different graphs are affected. Okay, I'm going to split this up into multiple videos. So the first video we're gonna tackle is going to tackle the idea of increasing and decreasing. So really, when we think about a function increasing and decreasing, it kind of means exactly what we expect it to mean. And that is, if I have a function that looks something like this and something like this, then what you'll notice is that it increased right here and it decreased right here. So increasing is when if you move positively in the x direction, the y goes up. Decreasing is where when you move positively in the x direction, y is going down. I always think of it as like a little man just walking. I guess it could be a woman. I don't want to offend any of our female students. So a man or a woman. How about a hobbit? So some man-like object is walking along this hill. And if it's going uphill, it's increasing. If it's going downhill, it's decreasing. And I think this tends to make sense. But what's important is from a calculus perspective, what do we know? Well, if it's increasing, that means we have a tangent line that has a slope that looks like this. And that means that our slope is positive or greater than 0. Versus if it's decreasing, then what does that mean? Well, it means the opposite. It means that our slope is negative or less than 0. And this is good because this gives us kind of a really nice way of thinking about when a function is increasing or decreasing. So if you look closely, you'll see, okay, I just have to figure out the derivative at every point, figure out which points the derivative is positive, which points the derivative is negative, and then sort them out. But I don't actually have to analyze every single point on the entire graph, so there's an easier question I can tackle. And it's this question of when does a graph switch from increasing to decreasing or vice versa? And let me just draw a quick graph here on the bottom. And so we can have a graph that looks like this. Maybe I'll put a little point here, and maybe I'll make it level off and come up. Okay, so when does our graph switch from increasing to decreasing? Well, I'm going to notice it's increasing right here, and it switches at that point. It's decreasing right here and switches at that point, and then it looks like it's increasing all the way along this point. But what do you notice about the 2 points where it switched? Well, it switched at points where we had what we called critical points earlier. It switches at critical points, which is where our derivative is 0 or our derivative does not exist. So those were the two cases, either the derivative is 0 or does not exist. Those are the two cases where we get our graph switching from increasing to decreasing. Notice you can have critical points like that one where the graph doesn't switch. So just because you get a 0 or does not exist, that doesn't mean the graph automatically switches, but it has to switch at critical points. It can't switch in the middle of a section while it has a positive slope or a negative slope. Okay, so this gives us a method for determining when a graph is increasing or decreasing, and I'm just going to call this the increasing decreasing method. This is my own wording, so people probably don't know this terminology outside of me. But what you do is you start by finding all critical points. So like this problem right here, we find all the critical points. So we'd find those 3 critical points. And then once we find those 3 critical points, we would place them on a number line. So what I would do with this problem is I would find those critical points. I would then draw a number line, and I would put those 3 spots on my number lines. So I would have my critical points, and I would mark them. And then once I have a number line, what I know is that if I look at this, I have 3 sections of my graph. Actually, I have 4 sections of my graph. And I know that inside this section, right, inside this section, I'm either always increasing or always decreasing. I can't be changing from one to another. So I can just test any point and figure out if that's positive or not. So I could just pick any point on here, find the slope of that point, and if it's positive, then I know every point in the whole section is positive. So test each section of the number line to see if it's increasing or decreasing. So I know that whole section's positive. Here, I get that it's negative, so that whole section is negative. Here, I would get that whole section is positive, and here I would get that that whole section is positive. So what I see is that my graph must be increasing, decreasing, and increasing, and continues increasing for that whole range. Now, if you have a graph, you don't have to do any of this work. So this type of picture is not for a situation when you have a graph, because if you have a graph, the answer is you just look at it and tell you when it's positive and negative. This is for when we have an equation and we're trying to make sense of the graph. So if you had an equation and all you had was this picture right here, you could turn this positive, negative, positive, positive into a rough picture of your graph. So if I gave you this and said, draw me a graph of my function, well, we're not going to be able to get it perfect, but we know a few things about it. And that is, we know our function must be going up here. We know it has to be going down here. We know it has to be going kind of up here, has to be kind of going down here, has to be going up here, and has to be going up here. So we kind of get this type of picture from our graph. Notice this isn't exactly the same as what we had, but it has the same kind of, some of the same basic elements. And as we finish today, we'll also talk about how to determine which way it curves, like how does the graph curve as we go through the function. And then from these pictures, we'll get a better picture of what our graph looks like. So this is what I'm going to call my increasing decreasing method. Find critical points, place them on a number line, and then test each section. And once you have that section, you can start to make a nice little picture. So let's do this on our first function. Our first function is f of x equals x to the fourth plus 8x cubed plus 18x squared. So the first thing I'm going to do is find my critical points. So I'm going to take the derivative of this thing, which is 4x cubed plus 8 to 24 x squared plus 36x. What are my critical points? My critical points are where this doesn't exist or where it equals 0. Notice it always exists because there's no dividing by zeros or anything. So I'm just going to take that equation and set it equal to 0. There are ways we could solve it. I'm going to just try to factor, and I'm going to notice, oh, I've got a 4x and everything. So let's factor a 4x out. And if I factor a 4x out, I have an x squared plus 6x plus 9. And then I'm going to try to factor that. And you can do your own factoring here. I'll notice that it's x plus 3 and x plus 3. You could have tried your own, done your own thing. I happen to just see this and recognize that it's a perfect square because if I take half of that number and square it, I get that number. And this was how we completed the square earlier. This is where our perfect squares come from. Okay, so there's that. Okay, so now what I need to do is I need to solve that equation. I changed my setup today, and I don't have quite enough space to slide my whiteboards around. You all can deal with it, though. And so what I get is I get either x is 0 or x is -3. So those are my two solutions. I get 0, -3, -3. So what's my next step? My next step is to draw a number line, and I'm going to put 0 on my number line, and then I'm going to put -3 in the number line. And now I just have to test every section. So what you'll see is that I have a section here and a section here. So I have 1, 2, 3 sections. So let's just test this section right here. So all I'm going to do to test it is I'm just going to pick some number that's less than 0. And so choose your favorite number less than 0. For me, my favorite number less than 0 is -1. -1 is a nice simple number to work with, so I'm going to use x equals -1. And I'm going to ask, is the graph going up or going down at -1? Well, how would you figure if it's increasing or decreasing? Well, what you would do is you would plug -1 not into the original function, but into the derivative. So I'm going to have this derivative equation, and I'm going to put -1 into it. I could use that equation. Why don't I use my factored version? It looks to me like the factored version might be easier to plug -1 into. Okay, so I get 4 times -1 plus -1 plus 3 times -1 plus 3. It's going to give me -4 times 2 times 2, so I think -16 is what I got. So what does -16 mean? -16 means it is decreasing. So what I usually do is I just stick like a negative sign here, and that negative sign just means that we're decreasing everywhere in that region. Okay, let me erase this and do the next section. Hopefully you have enough space where you can write them all out, but because I'm kind of on a limited whiteboard here, I'll just erase it. And now let's pick a point between 0 and -. Oh, wait a second. What am I doing? Guys, I put -3 to the right of 0. I have no idea how numbers work. Sorry about that. Let's start over. I'll put 0 here and -3 over here. Okay, now notice my -1 is still on here. The -1 is right here. So that means this part here is negative and this part is decreasing, but I still need to check this side and this side. Okay, sorry about that. That was a bit of a non-intelligent moment for your math professor, getting -3. I think I must have just thought it was +3 and just didn't think about it. Okay, so let's pick a number less than -3. What's a good number less than -3? -4 might not be bad, so let's choose -4. So I'm going to try this section, and I'll put -4 into it. So if x equals -4, I'm going to put -4 into the derivative, so I'll put it into this equation. Or again, you could put it into your original derivative equation. Any version of the derivative equation. They're all the same equation, just with some algebra. Okay, so I'll do 4 times -4, and -4 plus 3. -4 plus 3. Okay, this isn't too bad. Here's a -16. The good news is this is -1 and -1. And so I've got just -16. So what does that mean for my problem? It means I'm decreasing. So I'm also decreasing in this section. So we can see already that my picture is decreasing here and also decreasing here. Finally, I'm ready to test something bigger than 0. So 1 seems like a nice friendly number, doesn't it? So I'm going to put 1 in my derivative equation. And I'll get 4 times 1 times 1 plus 3 times 1 plus 3. It looks like I got 4 times 4 times 4, which happens to be 64. And so, so what does that mean? That means it's increasing. So I'll put a big plus over here, and I'll write increasing on this side. Okay, so now that we look at this, we can start to see what we should expect our graph to look like. So what should our graph look like? Our graph should be going down, should be going down some more, and it should be going up. So if I were to try to draw a graph of this equation, my graph might look something like this. I'll put 0 right here, and then I'll put -3 on my graph. Oh, -3. And let's just put some dotted line here just to kind of give me a little bit of guide. And I'm not exactly sure all the details of what the graph's going to do, but I know the graph is going to go down on this side, so it's going to be going down. I actually know it's 0 at 3, so it's going to flatten out for just a minute. But it's going to go down, and then somewhere around here, it's going to start to go back up. So it goes down, and back up. So we kind of start to get the picture of the graph. It's one, it kind of is down, but with this little slope, kind of a little roller coaster action over here, and then flips around and comes back up. Okay, again, in my second video, we're going to pay a lot more attention to not just when is it going up and down, but like what is the curviness of this as we go through from the left to the right. But hopefully this is making a little bit of sense. And I want to stop and ask a question. Do we have on this graph any maxes or mins? Well, it turns out we have no local maxes. But what about a local min? The answer is yes at x equals 0. So the question is, could we have figured out that we had a local min without drawing the picture? And the answer is yes, because if you look at our problem, you'll notice we're going down and then we switch to going up. And so a local min had to occur right here in this spot. Switches from down to up. So what that means is our graph had to come down here and up here. So no matter what the shape is, this spot must be a local min. Let's make this a little more precise. We'll make this a little more precise with what's called the first derivative test. And so the first derivative test just says that if we think about these points, so if we think about a critical point, where the graph switches from positive to negative or negative to positive, we can know automatically whether we get local maxes or local mins. So if our derivative switches, so if we have a number line here and we have this mark where we're switching from positive to negative, what does that mean for our graph? It means our graph is coming up on this side and then going down on this side. So what must be the case? It must be a local max. So you have to have a local max when you switch here, versus if I were to think of it as going from down to up, negative to positive, then that means your graph goes down and then back up. So that must be a local min. So once we've kind of done this increasing, decreasing test, once we've drawn out our number line and done our tests on our number line, we can tell instantly where any local maxes and local mins exist. Okay, this is really a great way of tackling problems and a great way of making sense of things. So let's move to the last problem that we're going to do for this video until we jump on for the second video. Our last problem is going to be problem 3.7. And what I want you to do is the normal thing where you push your pause button. There's my pause button. So push your pause button and take a moment and try this problem. Hopefully you can do it kind of well. Notice that the number line only goes from 0 to 2 pi, so you don't have to go the whole number line. You can start and stop at 0 to 2 pi. Okay. All right, we're back. We're doing this trig problem, and so our function is y equals, not y equals x plus 2 cosine of x. And so we take this derivative and we get 1 minus 2 sine of x. If this function looks familiar, it's because this is the one we did on the 5.1 video, so we've seen this before. And now we're looking for critical points. Critical points are where this derivative doesn't exist. Sine always exists. It doesn't have any asymptotes or anything. So we just need to figure out where it equals 0. So we need to set that equal to 0. So we'll do 1 minus 2 sine of x equals 0. I'm going to do this in one fell swoop by subtracting 1 and dividing by negative 2. So sine of x equals 1/2. And now we just have to ask, okay, what does that mean when sine of x is 1/2? Let me come and think about our number line. 1/2 is right here. Sine is the y value, so that's that point and that point. And it ends up, I think, being pi over 6 and 5 pi over 6. Okay, so good luck finding those. Hopefully that makes a little bit of sense because we did it the other day. But if you need help on the trig, don't hesitate to come talk to me. I could spend a lot of time with you working on trig. We can get your trig down. Don't let trig be the reason you're not successful this semester. Don't let anything be the reason you're not successful. Be successful. Let's do that. Okay, so let me come over here, and now let's start drawing that number line. So I'm going to draw, let me just write once again what our function is. Our function, the derivative of our function, was 1 minus 2 sine of x. And so let me draw that number line out. And notice, I said earlier, we're free to go from 0 to 2 pi. Notice the problem doesn't say to do it for all numbers. It says to just go between 0 and 2 pi. So we'll put pi over 6 on here. I'll put it about right here. And then 5 pi over 6, which is almost the halfway point. Okay, so now what we need to do is we just need to check. If you'll look, you'll see that we have 3 sections. 3 sections on our graph. We have to check this section, and this section. So I have to pick something between 0 and pi over 6. That's a little bit of a mess. Let's go from right to left. That'll be a little bit easier. So let's pick something over here. Let's pick pi. Pi is a nice number. So let's put pi in our problem. And that gives me 1 minus 2 sine of pi. Notice sine of pi is 0 because that's 0 at that point, so that is just 1. So what does that mean for this? That means this whole side here is a positive too. Let's switch colors so we can see it really well. That means this side right here is a positive, and that means we're increasing from 5 pi to 2 pi. All right, let's pick a section right between pi over 6 and 5 pi over 6. Pi over 3 might be a good choice, or pi over 4. I find students kind of like pi over 4. That's like, pi over 2 might be a really good choice. Let's do pi over 2. That looks like a good one. Because sine of pi over 2 is going to be a nice number for us to work with. And so f prime of pi over 2 is going to be 1 minus 2 sine of pi over 2. Sine of pi over 2 is 1 because it's the top of our circle, so this is negative 1. Okay, so that wasn't bad. So that allows us to, that means negative 1 means that this is negative in this section, and that means we're decreasing from pi over 6 to 5 pi over 6. Okay, now the part that I was trying to avoid, and that is something between 0 and pi over 6. Maybe pi over 12 is a fine number. And you know, I could, if I really wanted to, we could figure out pi over 12 because we could use double angle identities or half angle identities. But you know what I'm going to do? I'm going to use my calculator. And let's just do f prime of pi over 12 and see what I get. So let's come here, make sure you're in radian mode, and I am. So let's come here and do 1 minus 2 sine of pi divided by 12 and hit enter, and I got positive 0.48, so almost half, so positive 0.48. It doesn't really matter what the number is. The only thing that matters is that the number is positive. And so that's a positive number, and so that means we're increasing here. So we can see right now that our graph is increasing, it's decreasing, and it's increasing. We can also see where maximums and minimums are located. Notice here we go from up to down. So what does that mean about this point? This point must be a local max. Similar to this point, we go from down to up. So this point must be a local min. So when we switch from the derivative being positive to the derivative being negative, we get a local max. When we switch from the derivative being negative to the derivative being positive, we get a local min. Okay. Okay, so now we're ready to kind of try to put all this together and make ourselves a graph. And let me do that as best as I can. So let's get that. Here, tell you what, let's do it like this. And let's put our graph right on top of here and see if I can see just a little bit of this, a little bit of what's going on here. Okay, so what is my graph going to look like? I'll draw my line here. Let's go right here because that's 0. Let's put pi over 6 right here and 5 pi over 6 right here. And then I actually can figure out what 0 is because I know my function is x plus 2 cosine of x. So at 0, that's 0 plus 2 cosine of 0. Cosine of 0 is 1. So I actually start at 2. So let's just put 2 right here for our starting value. And notice what we're going to do. If we start at 2, our function is going to decrease a little bit. Let's make 2 a little bit higher on here so I have a little bit more space to decrease. So we're going to decrease a little bit, and then we'll increase between those guys, and then we'll decrease the rest of the way. And I'm not exact. Oh, wait. I did them backwards. Your math professor is struggling today. This is twice I made somewhat ridiculous mistakes. So 2. So instead of decreasing, we're going to increase. So we're going to increase for a little bit, and then we'll decrease between these, and then we'll increase on out. And again, we're going to spend some time next time figuring out like the curviness going on in between here. We'll make this picture a little bit prettier, but this is a nice starting point for today. Okay, come to the next video, and actually look at that picture at the bottom of 6.5. Look at those 2 graphs and see which one, what's different about them. See if you can articulate in words what's different about them. And that's where we're going to start the next video. So see you then.